So let me say it now because it's recording. Simplifying square roots will be on the exam as well. Basically, I'll give you a square root and I'll say simplify it. So that will be on the exam as well. You know, it was something we did after the first test. So all right. Okay, so this is another example, okay? You know, we have the domain again is 1, 5, and 6. The range is all the y coordinates. We have 2, we have 3, 3 is listed already. We have 8, 8's listed already. So we have this. You know, you don't have repetition in a set. So from here, right, we have 1 is going to 2. 1 is also going to 3. So we have 2 arrows coming out of 1. Same thing with 5, right? 5's going to 3, 5's going to 8. See? As you can see. We also have 6 going to 8. 6 also goes to 8. So we have another relation. It's not a function, though, right? Because again, 1 and 5 are inputs that have multiple outputs. Can't have that in a function. And again, really from there, you could see that certain relations are functions. In other words, you can make a special kind of relation is, in fact, a function. Basically, I mean, this is a little more precise, but a relation is a function if no two distinct ordered pairs have the same first component, have the same x coordinate. Right? In other words, suppose you have these two ordered pairs in your relation. The only way that could happen is if B and C are the same. Mostly because what this is saying is A would be assigned to B and A would be assigned to C. But if B and C are different, then A would have two outputs. Okay, that's probably confusing, I know, but another way of thinking about it is if in the relation all the ordered pairs have different x coordinates, different first components that is, then it's a function. Or if you want, you could just draw the correspondence diagram and see if that's a function. You know, you're seeing that we can represent a function in many different ways. So from a relation, you could also draw a correspondence diagram and see, well, this is a function because the correspondence diagram is. Or again, with a relation, if all the ordered pairs have different x coordinates. That's really what this is trying to tell you, just more mathematically. So, as an example, let's say we had this. Here are these ordered pairs, right? I mean, right away, even without all this here, you should be able to tell this is a function. All of these have different x coordinates, right? This one has 4, this one has 9, this one has 1. So all the x coordinates are different. And also, again, here's the domain, right? We have the domain is 4, we have 9, we have 1, right? The range we have is 7, 2, and 10. Now the y coordinates is the range, the set of y coordinates. And if we draw the correspondence diagram, we have 4 goes to 7. We have 9, that goes to 2. We have 1 goes to 10. Like so. As you can see. So here you can see also that each input only has one output. In other words, each element in the domain has one arrow coming out of it. Hence, we have a function. Another way of seeing it. Okay. Here's another one. Excuse me. So here also, this is in fact a function, right? Because again, even though even though the y coordinates are all the same, the x coordinates are all different. The x coordinates are all different, okay? I mean, here the domain is 491, right? The x coordinates. The range is just 7. There's only one thing in there, okay? But you can see that 4 is assigned to 7, 9 is assigned to 7, 1 is assigned to 7, right? But this is still okay. That's a function. Because again, each input only has one output. And that's what we want to happen. Each of these inputs have only one output. And that's what we want. That's okay though. Okay. Are there any questions on this? Well, is this a function? Well, although I guess you can see right here it says no, but it's not a function. Now, why is that? Well, notice again, from here, I mean, the correspondence diagram you could tell, but from this alone, you should be able to tell it's not a function. You have two ordered pairs with the same x coordinate. We have these two ordered pairs, right? 4, 7, 4, 2. But the x coordinates are the same. It's not a function then. And why is that? Well, again, if we drew the correspondence diagram, it's a little more obvious. Since we have these two ordered pairs, this is saying 4 goes to 7, and it's also saying 4 goes to 2. 4 goes to 7, 4 goes to 2. So 4 has two outputs. Something from the domain is assigned to two different things from the second set. And we don't want that. That can't happen for a function. Okay. So what's the domain of this? It's 4, 9, 1, right? The x coordinates. The range is 7, 2, 10 down here. That's what the range is. Okay. Good. So we have that. Are there any questions on this one? Okay, so I mean, that's what a function is. We'll see, I mean, I'm not done yet, but we'll see that you can actually define functions using equations and formulas and graphs. I want to look at notation now. Notation of functions is kind of tricky. I'm not going to lie to you. And I'll really explain it as best I can. For functions, right, we generally use letters such as these. F, G, H, capital F, capital G, capital H. Usually from the context, you can tell if it's a function or not. I did say capital letters denote sets, but from the context, you'll be able to tell. Usually letters such as F and G, those are used a lot to denote functions. And remember how in the definition we had little x from capital X, the domain? Little x will represent an arbitrary element from the domain. Okay, because again, we want to specify that rule. We want to specify what the function does. So usually, so little x will represent an arbitrary input, an arbitrary domain element. Okay, and what happens is, remember in the definition that the function takes x back and gives you back, normally it gives you back y, right? If you remember, let me see something, let me go back, right? If you go back here, remember how f takes an x, and what you get back, the output is y, which comes from capital Y. Okay, little y comes from capital Y, and y is assigned as output for x. Well, the notation for that, I mean, is this. Let me get to it. Come on. Oh, no, I messed it. Here it is. The notation you actually get for that is f of x. So f of x is actually how we denote the output. In other words, if x goes into the function, the output you get is f of x. And to really drive this home, what people do to really represent this whole situation is they write this, y equals f of x. That's kind of like notation for the entire definition. You know, x goes into the function f, you get back something in the set capital Y, right? Little y is what you get back in capital Y. And what exactly is that element? F of x. That's how this is read, f of x. In this case, we also say y is a function of x. If you remember variables, the idea is that y is a variable, right? It can represent elements in capital Y. It depends on x. You know, y is the variable that holds the output. It depends on x, which is your input. So we say y is a function of x. Y is the dependent variable. It depends on x. We also say x is the independent variable. You know, you need variables to represent numbers, right? Kind of like hold numbers in their place. X represents the input. Y is the output. And how do you exactly get y? Since it's the, how do you exactly get y? That's what this equation says. It's f of x. I mean, y is a variable since x is, but y depends on x. Okay, I know that was a lot, I understand. So also, when you have a relation that is a function, right? We had the ordered pairs here, correct? Well, if our function, say, was f, we would have the same thing. It's just that the y coordinate would be f of x. You know, the relation, I mean, not that one. Here, this is actually a function, right? As we said, the idea is that this function is assigning 4 to 7. It's assigning 9 to 7 as well. So in other words, we have this, where f is our function. And just like above, we write this here. Okay. You know, and this is just something else people write. I like writing this. The idea is that x goes into the function f. What you get back is f of x, y equals f of x. You know, it's something in the set y, which is usually the collection of real numbers. But we write y equals f of x. And the ordered pair we have is x comma y.